So line integrals have this property that they're additive. If we have piecewise smooth curves, so that each piece is smooth, then we are able to add the results of the integrals. So let me again go to the drawing board. Get my axes here. One of these days I'll come up with a consistent color for axes, I think. It's just like I grab whatever piece of chalk is available. So X hat, Y hat, Z hat. Again, we're going to go to the point 1, 1. But the path we're going to use to get there is we're going to go via C1 here. And then we're going to rise straight up. C2. And what happens, how additivity looks is the curve of some function over the line elements is equal to the integral of the first portion plus the line integral of the second portion, and so on, for however many line element components we have here. And so in this case, we're going to move across C1, which is a vector here. And let's see, C1, we can define with the parameter of I. Let's see, as our x value changes, our y value changes. So we'll do ti plus tj hat and 0 k hat as our parameter goes from 0 to 1, and C2 r of t is going to move. Let's see how this is going to move. We're going to be fixed at 1 I hat, right? Because we're fixed here, plus 1 j hat, and the parameter t is going to go up k hat. So we move from here to here, we stay fixed here, and we move straight up. And that'll happen also from 0 to t. So notice in parameterization, even though we're working our way across these two line integrals, as the t parameter moves, we're moving across this one while also going up this one. So our integral of the union of the two and again, we're going to use the same function we used before, is going to equal C1 dt, or ds, sorry, because we haven't put in our parameterization yet, plus the integral of C2 of the same function over this line integral. Oh, now I need to turn off my grids now. And this is equivalent then to going from 0 to 1 of my function with t0, because that's how my position vector is going. And I guess the norm, right, we'll take our derivatives v of t here. So that norm is going to be the square root. What do we have? 1, 1, and 0. So 1 squared plus 1 squared plus 0 squared, or root 2. And here it's going to be 0, 0, and 1. And so we have our norm. So the second integral then is going to be times root 2 dt plus the integral from 0 to 1 of f of 0, comma 0, or 1, comma 1, comma t times 1 dt. And now if we plug into our function, that means we're going to have t minus 3t squared plus 0 times root 2 dt plus 0 to 1 of 1 minus 3 plus t times 1 dt. So we're going to have let's bring our root 2 out front. And this is going to be t squared over 2 minus t cubed, evaluated from 0 to 1, plus t squared over 2 minus 2t, evaluated from 0 to 1. Or t squared over 2. Sorry. And so we do this evaluation here. We're going to get root 2 times negative 1/2 minus 1/2 minus 2 minus 3/2. And so this is root 2 over 2 negative minus 3/2. And notice this is not the same value as the line integral we did before. The path makes a difference. The path you take makes a difference. And even though the function is over the same function, the path we take through space and that function comes across gives different values. So line integrals work based off of the path you take, and path selection will become important for us. Let's look at one other shape here. Again, I'll do these in smaller videos. I'll do another chunk, and we'll look at another example here.